Okay, so this video is going to be on scientific notation. I'm sure you've all seen scientific notation before, but this video is going to show you why it is necessary, especially as we get further into chemistry. So scientific notation, the reason that it's necessary is that it saves us the trouble of having to write out super long numbers with a bunch of zeros, such as, I'm not even going to try to read these numbers, okay? Such as those numbers. Okay, it also allows scientists and mathematicians to omit insignificant zeros and just write out the significant figures because those are the numbers that are important to us. So this is where the sig fig rules, especially the zeros, so rules 2 through 4 come into play. So remember, leading zeros are never significant, never ever significant, okay? Trailing zeros are significant if there is a decimal point. If there is not a decimal point, the trailing zeros are not significant, such as in this number, okay? And this number has a bunch of leading zeros, so these zeros are not significant. And then if a zero is smushed between two non-zero digit bookends, then it is always significant, okay? So scientific notation, we are just writing the significant figures, okay? We're omitting the non-significant zeros. So here's the process of putting a large number into scientific notation without using your calculator, okay? So for a number like 103 million, we write the significant digits. So that is the first step, okay? So 103 is what we write. Then, number 2, we place a decimal after the first significant digit. So after the 1 in the 103, or whatever the first significant digit is, okay, you put a decimal point. All right, number 3, to make 1.03 look like 103 million, because those two numbers are not very close, it must be multiplied by 100 million, or 10 to the 8th. Okay, so then 103 million in scientific notation is 1.03 times 10 to the 8th. And that is a whole lot easier to write and understand than writing out all the insignificant zeros. Okay, so here is another example with a large decimal point, or I guess a small decimal point, but a decimal point with a lot of leading zeros. Okay, so write out the significant digits, or the significant figures, just like we did in the first example. So our first, remember, leading zeros are never significant, okay? So our first significant digit is this 4 right here. So we start with the 4, so we write 408, okay? Those are our significant digits, okay? Number 2, we place a decimal after the first sig fig, just like we did in the first example, so 4.08, okay? And then 4.08 is not close to 0.0000408, okay? So it must be multiplied by 1/100,000, or 10 to the negative 5, or 10 to the negative 5th power, okay? So 0.0000408 can also be written as 4.08 times 10 to the negative 5th power. Okay? All right, couple things to remember. The exponent is positive for numbers greater than 1. So if we have a bunch of trailing zeros and it is greater than 1, okay, the exponent, so the number right here, is positive. Okay, the exponent is negative for numbers less than 1. So the numbers that have a bunch of leading zeros that are insignificant, those are less than 1. The exponents are negative. Okay, so a couple more examples with 103 million. Move the decimal point 8 spots to the left to get 1.03, which is why it is 10 to the 8th. Okay, it is the number of decimal point spots that we are moving is the exponent. Okay, so with 0.0000408, we move the decimal point 5 spots to the right this way to get 4.08. So you multiply that by 10 to the negative 5th, and that is how you get negative 5 as the exponent.